Good morning, everyone. Let's go ahead and get started today. So let me open up the notes. Hope everyone's having a good morning. Yeah, so we were in section 1.3 yesterday. Been talking about matrices, and we talked about computing determinants and kind of some geometric applications for computing determinants by finding areas of parallelograms or volumes of parallelepipeds. And we did this little example with computing the area of a triangle, which was kind of an indirect application of that formula. And then we started talking about cross products. This gives you a couple of things. First of all, it gives you this vector, which is orthogonal to both of the vectors that you start with. And it has this property where when you flip it, when you flip the order of taking the cross product, you're flipping rows in a matrix into the determinant, so you just get a negative sign. Basically, it gives you the other direction that's orthogonal to U and V. And we talked about the right-hand rule, which is hard to draw, but is something you can look up in the textbook. We also learned that the cross product, when you take the magnitude of it, like if you think of the length of this, also gives you the area of this parallelogram, which is different than this formula up here, because remember, the area of this parallelogram was in two-dimensional space. So these are both two-dimensional vectors, right? So we're living in what we would call R2, because they're two-dimensional vectors, whereas these vectors are in three-dimensional space. So this parallelogram is just floating in three-dimensional space. And you can find its area using the cross product, the magnitude of the cross product. And in that vein, basically both of these are going to have the same length. So the magnitude is going to be the same for both of these vectors, V cross U or U cross V. Okay, so just a quick summary of what we did yesterday. But then there's another word we want to use when describing this sort of cross product here. So we introduced this new word with respect to a plane, which is to say that there's a vector that's normal to the plane, which just means that it's orthogonal to all of the vectors that live along the plane, right? So here in my picture here, I drew it as just being a right angle with the plane itself. But basically you can draw, right, all of these different vectors that live on the plane, and this is going to form a right angle with those. And so, yeah, you can kind of picture different way. So for example, I have here like a piece of cardboard, and you can put like a pen there, and that's acting like your normal vector. That's kind of how you should picture it. Okay, cool. And the way we use this is when we're going to start talking about equations for planes, because last time, I think on Tuesday, we talked about parametric equations for planes, which was like something having to do with S and T. There's some problems on it in the homework, but all of those planes go through the origin. And we want to talk about just planes floating anywhere in three-dimensional space. And to do that, we need the concept of a normal vector. And so we're going to see that formula here. So if we have a plane containing a certain point and a normal vector. So I'm going to give you guys a second to write this down. And as you're writing this down, I'll kind of explain conceptually why we need these two pieces of information. So here we have a point and the normal vector, and you get this equation for a plane. And the reason you need that information, let's think about what we have. Right, in two-dimensional space, if you have a point and a slope, then you can concoct a line. And this is kind of related to that, right? We also talked about taking a point and a vector in two-dimensional space, and that gives you a line, right? But in three-dimensional space, the normal vector completely determines the plane up to kind of where it's sitting space. It kind of determines the angle of the plane, if you will. So it kind of determines like, is it going to be like this? Is it going to be kind of like rotate here? Do it again with my little piece of cardboard. Is it like this? Is it kind of this angle, you know, kind of how is it sitting inside of space? And the normal vector is basically gives you all of that information. Okay, and the plane just says, okay, is it here or is it up here? But it's still in this. You see how this pen is not changing direction at all. It's just kind of changing where it is. Okay, so the point tells you. This tells you where the plane is, and this tells you kind of the angle or what direction. Angle of the plane. Okay. And then this formula kind of combines all of that into just one nice formula. And points x, y, z that satisfy this point, this formula are points that are on the plane. So let me explain why that is. So let's imagine you have this plane living in, you know, your three-dimensional space. Let's say this point here is your, actually I want to make this a little bigger. So let's say you have something like this. So this plane is living in three-dimensional space. Okay. There's a point on, this point is the point that we have on it. So x naught, y naught, and z naught. And then we want our normal vector. So our normal vector is over here. So this here is n. Okay. So we want to figure out why this formula is true. Like, where's this formula coming from, right? It's always nice to have some information, some idea of understanding of where these formulas come from for a couple of reasons. One, I think the biggest reason is so you don't feel like you're just memorizing a formula, right? Whenever you, I don't know, for me, whenever I feel like I'm just memorizing a formula, I never learn it as well. I never internalize it as well. Blindly memorizing, I feel like it's one of the hardest things to do. What's easier is to have some understanding of where the formula is coming from, so that, first of all, I understand what all the parts mean. And second of all, I, in a pinch, if I do forget the formula outright, I can reconstruct it if I absolutely need to. Though usually it's going to be more like, it's just going to kind of, I'm going to forget certain parts of it. And the construction, knowing where the formula comes from is going to give me some hints as to kind of what that missing part is or something like that. That's usually why I like learning the information behind these formula. So this is your point x, y, z. This is the point n. So if we want to say, okay, any point on here should satisfy a certain equation, what should that equation be? So this point here is x, y, z. How does this equation relate to n? How does it relate to x naught, y naught, z naught? And what does that mean? Well, we want this vector to be orthogonal to the vector that we get drawing like this. So we want this vector here to be orthogonal, right? But what is this vector here? Okay, well, it's anytime we have a vector connecting one point to another point, we can cook up, how do we cook up the coordinates for this vector? What do we do? How does it relate to these 2 points? How can we get this vector here? So you're thinking there of the parametric equation for the line. We want to think more. So we have 2 points, and we want to connect them with a vector. Yeah, so we're going to subtract the corresponding points. So if it helps thinking of, you know, like the origin lives out here somewhere. Here, let me do this in a different color. So you have like the origin living out here, and you have like this connects to here and this connects to here, and you're thinking of them as vectors, then this red vector is the difference between these 2 vectors, right? And the coordinates of these 2 vectors is just the coordinates of these 2 points, right? So all of that to say that this red vector is just the difference between these 2 points. So x minus x naught, y minus y naught, and z minus z naught. Okay, and we want this to form a right angle here. In other words, we want it to be orthogonal to the normal vector. Does anyone remember, like, in terms of algebra, in terms of the formulas, what does it mean for two vectors to be orthogonal? Okay, geometrically, it means that they form a right angle, but in terms of the formulas, does anyone remember what it means for two vectors to be orthogonal? Yeah, the dot product is 0. So if I take n dot with my red vector here, if I gave it a name, it would be easier. N dot with this vector here, I should get 0. Well, n is just ABC, and the other vector is given here. So if I do exactly that, so I take A, B, C, the dot product with x minus x naught, y minus y naught, and z minus z naught. Well, if I take this dot product here, because I want them to be orthogonal, I should get 0. But what's this dot product here? What happens when I take this dot product? I get A times this, B times this, C times this, and I add that all together. Well, I just get this formula back, right? So this relates back to this formula here, right? If I took that dot product, right, I would just get that formula back. Okay. Any questions on that sort of process? So this is the equation for a plane. This is typically the form you'll see it in. If you're given a point and a normal vector, this is the formula you'd use to just plug and play. But sometimes you can see here that, you know, the x naught, y naught, z naught are just going to be a number. ABC is just going to be a number. So you're just going, if you distribute all this through, there's a simpler form. So there's another form that you can sometimes see this in. So sometimes, actually probably more commonly, it's going to be in this form. If they just say, here's the equation for a line, it's usually going to be in the form ax plus by plus cz. So basically all we've done is distribute this a through, distribute this b through, distribute the c through. Then we get a bunch of stuff that is basically just a constant at that point, right? When we actually go through and do this arithmetic, this just gives us a number. So we can just say plus d equals 0. And this d here, you can write in terms of all of these stuff, right? But it's just some number, okay, at the end of the day. So sometimes they just give it to you in this form here. Cool. Any questions here so far? So this is going to be how we describe planes in three-dimensional space. It's the equations that basically are, we call these linear combinations of x, y, and z. What that means is that you just take x, y, z, no exponents or anything, just x, y, z, and we multiply them by these three constants. And then maybe we add on another constant and set that equal to 0. Sometimes they also move this capital D to the other side. And so it's ax plus by plus cz equals, again, just some constant, some other number, right? So it's important to recognize, like, if I give you an equation, you should be able to say, oh, look, that's the equation for a plane, okay? I mean, the key thing is just you have ax plus by plus cz. Again, some parts of ABC might be 0, so you might not see a y, or you might not see a z, or something like that. Okay, cool. Any questions? Okay. Sorry. Okay. Okay, so now the last part of this is so basically you have the concept of a plane living in three-dimensional space. This last little formula here is a convenient way to get, so if you have a plane living in three-dimensional space, okay, that's not a very good plane. Okay, and then a point just hanging out here, also in three-dimensional space. The question is, how far is this point from this plane? Well, you might think, oh, just take some point on the plane and measure it. But right, if we took a point out here, this distance would be too much here, right? Because there's clearly a point if I just get closer over here that measures it better, okay? Okay. And this formula here gives us exactly this length here, this here. So this here is the distance from the point to the plane, okay? So here we used x1, y1, and z1. And see here, we gave the formula for the plane is in a different form. It's ax plus by plus cz. And we set that equal to d here, okay? Okay. So this one I think is a little more complicated to explain where this formula is coming from. I think there's a good explanation in the textbook. So if you want to see an explanation of this, you can look for it in the textbook. If it's not in the textbook, it's definitely somewhere online. I think I was looking at the Wikipedia page at some point to kind of prepare for this. And I think there's some explanation there too. Someone's asking, what's the difference between like the absolute value symbols and the double absolute value symbols? That's a good question, and I think it's worth discussing here. So so something goes in between the absolute value symbols or versus something which goes in between these double absolute value symbols. So this one on the left, right, this is like I'm saying, this is the absolute value. And here you plug in numbers. Right? If I plug in a number here, you just drop the negative sign if it has one, or leave it alone if it doesn't, right? Over here, this is the norm. This, you plug in vectors. Okay? So if we look so specifically, this person mentioned Cauchy-Schwarz inequality for this one and the distance formula for this one. And so if we look at the context of, I think I'm going to keep these same slides. If we look here, look what we're doing. A, B, and C are numbers. X1, Y1, and Z1 are all numbers. So when I do this arithmetic here, this is just going to give me a number, but it might be a negative number. So we throw on absolute values to just make sure it's positive, right? This is the absolute value you know and love from pre-calc. The norm, on the other hand, let's see if where does it come up? I'm sure it's in the slides here somewhere. Here, right? This V cross U, remember, is going to be a vector in three-dimensional space, and we want to get the length of that vector. So this norm here is the length of the vector. Okay, so this is the length. So this is the maybe like drops a negative sign here. Negative signs. And this one gives the length of a vector. Now these are related. They have a lot of similar properties. For example, both of these will always be, will never be negative numbers, right? You can never plug something in and the output is negative to either of these, right? This one has a square root in it, and this one is just you're dropping the negative sign. So the alternative thing you can think about to see how these are related is the absolute value you can think of as this is like this, like the norm for one-dimensional vectors, which is a little weird to think about one-dimensional vectors. But if you think of like a point on the number line as the vector from the origin to that point, right? The length of that vector is going to be just the absolute value of that number, that point. Okay. Cool. Yeah. Cool. Hopefully that helps clear that up. Okay. So let's move on to section 1.4 here. Section 1.4. Let's open that. It's going to be about cylindrical and spherical coordinates, and I have some cool little drawings here. Okay. So this is this chapter, or this section, will be all in three-dimensional space. With the exception of the first slide, which is a review of polar coordinates, right? So in two-dimensional space, we call it two-dimensional space because you need two numbers to tell any one point, to tell where any one point is. So for example, this point here, x comma y, you need two numbers, but those numbers represent something specific. So here it's, if we have I'm picturing like a square here, which is telling us this x and a y in the form of this distance here is x, this distance here is y, right? And that's where this x comma y is coming from, okay? And in polar coordinates, you're still using two numbers, but where those numbers are coming from is a little different, okay? So in this case, you'd say, okay, we can just connect it with a line to this point. We can connect to this point with a line segment from the origin. And that distance from the origin there is r, okay? And this theta here is coming as this angle from the x-axis. So we always go off of the x-axis. You might remember that from your pre-calc days. Is angles are always measured from the x-axis. That's just a little convention that we use. And that's our polar coordinates. You still need two numbers, but the numbers represent different things, okay? And so the same point in Cartesian coordinates is going to look different in polar coordinates, right? It's going to look different in terms of the pair of numbers you use. But if you're plotting them based on what these numbers represent, you'll get the same point in space, okay? So here it's the same point, just the numbers represent different things, okay? Simple enough, but we also want to be able to go back and forth between them. So the easier direction to go is if I give you polar coordinates, we can get to Cartesian coordinates, right? We just need to write x and y in terms of r and theta. So if you give me some r and theta, how do I cook up x and y? You might remember this from whenever you learned about polar coordinates. Does anyone remember these formulas? So how do I write x in terms of r and theta? So if you remember your unit circle, that gives you the theta part. So if you remember your unit circle, the x coordinate was cosine of theta and the y coordinate was sine of theta. Does everyone remember that from their unit circle? Again, we mentioned pre-calc the other day and how you might need to brush up on some of that. Yeah, and then so once you have this r, you multiply r by the cosine of theta and the sine of theta. A couple people coming in there with the answer. Yeah, so this is, I say this is the easier one. It does look a little, it is maybe like a little more straightforward in terms of the formula. It's just this formula here. Going in the opposite direction is a little trickier. So let's see. Change color here. So going from Cartesian to polar is a little trickier. The first part is pretty easy, right? How do I get r, right? Just based on my picture here, geometrically, I can figure out how to get r from x and y, right? If I plotted this length x and y, and then I also plotted r, that just gives me a right triangle. So how am I going to get r here? What theorem will I use? Maybe the only theorem that you've known like forever. You have a right triangle, trying to figure out, yeah, so you can use the Pythagorean theorem. I think you spelled it correctly too, which is bonus. X squared plus y squared equals r squared, or just r equals the square root of x squared plus y squared, right? So that's not too bad, right? You can remember that by using the Pythagorean theorem. Just draw all three of those values and like, oh yeah, it's just a right triangle. Use the Pythagorean theorem. The angle is the harder part to get. And this is the one that it's going to like depend on the quadrant you're in. But the idea is basically that theta, this has to do with the fact that inverse trig functions only have a certain range, right? We talked a little bit, we talked a little bit about this with some, when we were talking about, at some point, when we're talking about the angle using the dot product, right? That formula involving the dot product and cosine of theta. When we solve for theta, there's like a cosine inverse, right? And so it only gives angles between 0 and pi. But in this case, we don't want to restrict to 0 and pi. We want to go from anywhere from 0 to 2 pi, right? And so this one's actually going to depend a little bit on what quadrant you're in. So we're going to use arctan. Arctan because it tends to be the most straightforward, because it doesn't involve, because basically if you notice this formula here and you try to go the opposite direction, you can divide y by x and the r's cancel, and then you just get sine of theta over cosine of theta. So I guess the note here is that tangent of theta is x over, or y over x. So we're going to use this to cook up the inverse down here. So it's arctan of y over x, and you might think, oh, well, that should be enough, right? But remember, arctan and tan are not arctan inverse. That's the inverse is already part of arctan. Okay, so remember, arctan, it doesn't spit out any possible angle. It only spits out angles between what is it? Negative pi over 2 and pi over 2. So this one is going to be, you're going to have to add some stuff here. So actually, let me give myself more room. Okay. Let's see, about there. So you're actually going to have different versions of this depending on what quadrant you're in. So if you're in this first quadrant, then you can just leave it alone. So if xy is in quadrant 1, right? Remember, we have 1, 2, 3, and 4. So I guess the important thing to remember is that the output of arctan is always going to be between negative pi over 2 and pi over 2, right? That's if you, again, brushing up on some pre-calc, some trig there. If you don't remember this, write it down now and just like take my word for it, and then maybe later as you're studying, look that up and try to remember why that's true. Look at the graph or whatever. But basically but we want theta to be between 2 pi or 0 and 2 pi, right? And so it's important to know what this angle is giving you. And if you break that down here, basically what that's going to give you, arctan of y over x is going to, if you're in, let's see. Oh goodness, now I'm gonna blank on it a little bit. So all of these are going to involve arctan of y over x, but what that's giving you is actually what we call the reference angle off of the x-axis. So for example, if it's in quadrant 2 or 3, it's going to be giving you, so for example, if your point was up here, if your x comma y was up here, arctan of x over y is going to give you this angle here. Of y over x, I should say, is going to give you this angle here. Okay. So, is that true? Okay, now I'm blanking. I should have written this down. Yeah, this is one of those things that I have to refigure out every time. This is why it's important to remember like why things are true. Oh, of course. Okay. Let me try to. Okay, so that's giving me trouble. Yeah, so this is important because it's gonna, if we do the work now, then it's gonna make our lives easier on the next slide when we actually start talking about three-dimensional stuff. Let me find the formula here. Okay, so this is in, okay, yeah, so that just reminds me. So this is in quadrant 1 or quadrant 4. Okay, this arctan, just leave it as arctan. Leaving it as arctan will work. Though this might give you the negative, but that's fine. Like it's still this, it's still measuring this angle here, here, and then for quadrant 2, you add a pi. And then for quadrant 3, you subtract a pi. Okay. So basically what this is doing is it's giving us basically a different way to figure out what the angle is here. Okay. I think the easiest way to see this, right, is if you get the arctan function, like I said, it's always going to spit out something between negative pi over 2 and pi over 2. And this won't give us this, like for example, in quadrant 2 here, it's going to give us this angle here. Actually, it might give us this angle here, I think, which is why we have to add pi to it. Or it's going to give us this angle. I see. It's going to give us this angle here, but it's going to give it to us negative. Okay, that's what it is, right? So if you plug into the formula here, it's going to give us this angle, but it's going to give us something negative. If we're in quadrant 3, it's going to spit out something negative, which is why we add pi, because we're just going to take pi, which is over here, and subtract by this. Okay. I taught pre-calculus last year, but it didn't. It's been a while, so I remember teaching them this when we were talking about the unit circle. Basically, arctan of this point right here is going to spit out this angle, but negative. And so you add pi, but secretly there's a subtraction happening when you actually do the arithmetic here. Okay. And now points in this quadrant here, in the third quadrant here, the arctan function will spit out, I believe this angle here. Yeah, so the book, it's a little different. So I will say that there's other ways to do it, and if the book, it's slightly different. If you subtract pi, you can also add pi in quadrant 3. Hold on. Let me make sure I got that right. Yeah. You can. I think that's right. I think I'm saying what it is now. Okay. Sorry, I should have. This shouldn't be happening. This is what I remember. So sorry if you already wrote this down. Let me use a different color so you can see what I changed. So you can use this formula for quadrant 2 or 3. Basically, it gives you in this up here in quadrant 2, it's giving you a negative angle, so you're subtracting from pi. But in quadrant 3, it's giving you arctan is giving you a positive angle, so you're going to add to pi. But then in quadrant 4, it's going to give you, so this point here is an example. It's going to give you this angle, and it's going to give it to you negative, right? So it would work on its own, but in order for us to get an angle between 0 and 2 pi, we add 2 pi to that, even though, so I'm writing plus, but there's a subtraction happening because we get a negative out of this arctan. This arctan gives us something negative. Yeah, so this is the formula I actually wanted to land on. Wikipedia says something a little different, which is what I was using here. But I think this is this is closer to what the textbook says, and I think I like that better. So we'll stick to that. Okay. Sorry about the confusion. I should have been more prepared for that one. But we got there eventually, right? We worked together, we got there eventually. Basically, the arctan alone won't give us the angle. We need to adjust based on what quadrant where we end up in. So this does take, you can either memorize some formulas or stuff, or it's going to take, every time you do this problem, a little bit of reasoning about where the angle is, right? So if you get if you plug in arctans of something to your calculator or your graphing calculator or whatever, and you get some number and it's negative, you should try to figure out what angle that is giving you and adjust appropriately, either by adding pi or 2 pi. And this is just kind of a systematic way of doing it. Okay, cool. So now you might be thinking, okay, you said you're going to talk about 3 dimensions, and we're talking about 2 dimensions. And that's because the first 3-dimensional coordinate system that we're going to learn about that's not Cartesian is cylindrical coordinates. So, so cylindrical coordinates is basically just polar coordinates on the XY plane, and then you just tack on the Z like normal. So we can, let's see, let me give myself some space here. Then we'll take a break after I kind of explain this, and then we'll come back and do the other coordinate system and some examples. So here, if we're going from cylindrical to Cartesian, then we have basically the same thing as we had before. Let me get this closer. Which is x equals r cosine of theta, y equals r sine of theta, and then z doesn't change. Z is the same as z. Z is the same in both of these coordinate systems. okay? So like I said, cylindrical coordinates is basically you take your polar coordinate system on the XY plane and you just add a Z component. You just tack on the Z component. And so the conversions are basically exactly the same, except you know, Z doesn't do anything. So here you have R equals X squared plus Y squared. Theta is all that trouble we just went through in the previous slide, right? You were probably thinking like, why is he going through all this trouble? It's because it's the same down here. Same as polar. Okay, I won't write down that monstrosity, but it's the same. And then Z again is just equal to Z. Okay, so we have these two. This is the new three-dimensional coordinate system that we'll introduce. Okay, cool. So far, this one, the reason we start with this one is because, ostensibly, the polar coordinates were a review. But as you can see, it's, some of the formulas are still kind of tricky. You have to remember some of your trig. But the concept is a review. And so cylindrical coordinates are just building right off of that into three-dimensional space. Okay, so just treat the XY plane, which, remember, the weird part about some of the coordinates, about the coordinate system we use in 3 dimensions is that the X is right here, Y is over here, and Z is up here. So this is still the same X, Y, and Z, which is why the angled part is down here. So if I was going to start labeling this, and I will here, this angle here is theta. That angle there is theta. And of course, this distance here is R, and this distance here is Z. Here you have X, Y, and Z. Okay, that's where your coordinates are coming from. Okay. Yeah, so back to where we were. Cylindrical coordinates. These are conceptually very similar to the polar coordinates in 2 dimensions. It's just that you have this extra Z dimension that just stays the same between Cartesian and cylindrical. Okay. So you can kind of just treat it as like polar coordinates plus a Z. And so that's kind of all that's happening here. You're treating the X, Y as polar and Z as itself. Yeah, and we're going to see kind of why we would want this other coordinate system in a bit. But next here, we're going to introduce spherical coordinates here. So these are a little more complicated, but we have a similar concept here that we're going to see in the in the pictures here. Let me just get, okay. So here what we're going to see is that again here on the left you still have your X, Y, and Z, but over here, right, you no longer have your R and Z. You have it's similar to cylindrical coordinates in that you're still measuring this angle here, theta, coming off of the x-axis, but you're, instead of measuring this distance here, you're measuring this distance here, rho. Okay, this distance here, which is actually more like the R that you would use in polar coordinates, because it's the distance from this point to the origin. So this is like the distance from this point to the origin, and we'll see in the conversion formulas exactly how that comes into play. But the last thing is this Greek letter phi. So actually, let me spell that out a little bit. So this, I said it out loud. It looks kind of like a P. It's actually the Greek letter rho, which would have been an R. So Think it's almost like a lowercase r in that sense. But you can look up RHO rho in Greek alphabet, so you can see how it looks when it's typed up on a computer. And this is just how I write it. It's almost like a P with a little extra hook in the bottom, but I tend to draw it kind of like almost like an S, but you loop the top part background and it touches itself. And then this other one here is the Greek letter phi. This one you may have seen before. PHI. It's also sometimes called phi. And you have this, it's a circle with a line through it. Sometimes they also use this, when it's typed, it sometimes looks like that. I should say like that. I kind of prefer it like this, but I think our textbook uses this, and so I'll do it. But I think Wikipedia uses this, which is even more confusing. These are these two, what these symbols are. What they represent is, again, theta is just this angle, rho is this distance, phi, kind of confusingly, is the angle from the z-axis. So it's this angle coming off of here. So this here is our phi, okay? You almost expect it to be this angle here, but it's actually this angle here, okay? I think in physics or in some disciplines, some engineering, I think sometimes this is called the azimuth, which is a fancy name that you'll never use again. I believe that's what it is, what it's called. Okay. Cool. One of these angles is the azimuth. I might be wrong about it. In any case, you want to be able to convert between these. So I think in this case, if we go from spherical to polar, or to Cartesian, spherical to polar can be a little trickier. It's actually probably best to just go from spherical to Cartesian and then Cartesian to polar if you need to. But the formula here is going to be kind of similar. You're going to see some similarities between this and the polar coordinates, or the cylindrical coordinates, I should say. But it's not going to quite be exactly the same. So you can do it using trig here and figure out what everything is. But what we get here is, so z is going to be r times cosine of phi. Okay. No, not r. It's going to be rho times cosine of phi. Y is going to be rho sine of phi cosine of theta. Nope, that's sine of theta. At some point I had these pretty well understood in my head, and now I have to double check, mostly just so I don't give you guys wrong information. So that's this here. That's going to be that here. Actually, I think I mixed up my phis and my thetas. Okay. I definitely did. So, then this is phi, and this is phi. Okay, so let me pause for a second, let you catch up on writing this, and let me explain how I realized that I mixed up my phis and my thetas. Basically, what you can what you can see here from the picture is that you get this right triangle formed by rho, the z-axis, and this distance here, which is the same. Oh, that's not the right distance. It's actually something like this. It's coming in. This distance here, we get this right triangle, or you could drop this down and think of this right triangle here, where this this here is z, this here is this, the hypotenuse is rho, this leg is z, and this other leg is r. So basically what this tells you is that r from our polar, r is coming from our polar coordinates, r is equal to rho times sine of phi. Okay, you can use trig to figure this out. Okay, and then so you can just take your formula, and then I guess z is rho cosine of phi, and that's how you get this formula. So you can combine these two with the stuff you saw in the polar coordinates, and you get these formulas here. Okay, again, I like to give you the formulas, but I also like to explain them when I can, because it can help with the memorization process, and two, it can help you double check to make sure you memorized correctly. Or if you forget a certain part, like I did, I kind of flubbed there. I realized my mistake because the x should have a cosine of theta and the y should have a sine of theta because of polar coordinates, right? That's how I caught my mistake there. Okay. Cool. Cool. So in fact, it's actually probably easier to go through polar coordinates. I mentioned earlier that you should go through Cartesian coordinates, but actually I'm taking that back. It's probably easier to go straight from spherical to polar using a formula like this. Okay. Now going from Cartesian to spherical coordinates, again, some of this might come from our understanding of the polar coordinates. But you can get the rho here is probably the easiest, because the rho is just the distance from the point to the origin, which is just the square root of x squared plus y squared plus z squared. Okay. Now these other two are going to be trickier. Theta we've seen before. And phi is new. So theta we've seen before. It's basically so same as cylindrical and polar. Okay. And phi is the new one that's going to give us something interesting. This is going to be yeah, so we can think of, again, I think this right triangle here is the key. We want this angle here, so we need if you look at this right triangle here, then we do opposite over adjacent for tangent, so it gives us z over, or no, that's r over z, but we want it in terms of x and y's, so it's arctan of r, which is the square root of x squared plus y squared, over z. Okay. That's how we get all of these three values. And notice this one, we don't have cases based on what's going on, right? This one is just arctan. We don't have to add pi or 2 pi depending on the quadrant or whatever. right? That weirdness goes away, and you might be wondering why. But let's think about what phi could possibly be. If it's straight up, if your point is on the z-axis, on the positive z-axis, straight up here, then phi is 0 degrees. Hold on. Now I'm doubting that, what I just said. Oh gosh. It should be so basically it goes from 0 to pi is my point. So here phi can't be any bigger than pi, but I should still be offsetting this by something. So I should be doing something like plus pi over 2 or something like that. And that's just going to make sure that I get something between 0 and pi. Okay. So if you get something in the calculator that's negative, this angle should never be negative. Yeah. Actually, I'm going to delete this. Sorry, I really should have double checked all of this stuff and had it ready for you a little more confidently. But so now I'm seeing what they do. But basically, straight up is going to be an angle of, for phi, it's going to be 0, right? And that's going to check out here. Basically, straight up, this is going to give us 0. And so we want it to be straight up, but then it can go back and it can go negative. So basically, it goes from back to front here, okay? Or, now I'm doubting. Why am I doubting everything? Uh, 0, 0. Yeah, I think I'm going to put that plus pi over 2 back. What does the textbook say? Does anyone have the textbook open? And want to tell me what the textbook says? Okay. But so the idea here is that you just use the arctan, but I think it's going to be offset by a pi. So I think I'm going to have to add pi here, or pi over 2. Just to make sure that we get the correct angle. Because it should be, straight up should be 0, and then it should go down to below the XY plane here, okay? Yeah, that's going to be correct, right? So 0 would be straight up. Phi of 0 should be straight up. Yeah, no, I think it is going to have to be cases, basically. So you're going to use the arctan function, and is basically what I'm trying to get at. But the specifics of how you use the output of that should have written down here for you guys. But I will definitely have it cleared up in the notes here before I upload them. Yeah, so basically it's using the arctan function. The exact formula I will get for you. Actually, right now I have the textbook pulled up here now. It, of course, doesn't have it written in the textbook as a nice formula. Okay. Yeah, so I think it's the arctan function, and then I think depending on what the angle actually is, it helps to draw a picture, and then you figure out whether the angle should never be negative. So phi should always be, I guess I'll point that out. Phi should always be between 0 and pi. Right? If straight up is 0, and then straight down is pi, and then everything else is right in between. It goes from 0 to pi. So I picture it like going like this, 0 to pi. Okay. The problem is that arctan doesn't necessarily do that. And so if it gives you something negative, then that means that you're actually down here. So it would be like plus pi in that case. Okay. Yeah, sorry about that. I don't know why I'm getting so caught up with that. Usually it's not a problem. Okay, let's get to some examples while we still have time. So there's a few different types of examples that we can do here. To start, we're just going to do like the straightforward. Let's convert from. Oh, someone's asking if I could explain this theta. So the theta is going to be the same formula that we used up here, which was the same formula that we used. Here, right? Which is kind of nasty. It depends on what quadrant in the XY plane you're in. I think I'm going to jump to an example because I think that's the easiest way to see exactly what's going on. Okay. So for example, here we want to convert the point 111 into cylindrical and into spherical coordinates. Okay. So let's move this here. So if we were to draw this point 111, okay. And this and this. So if you have a point, let's say 1, 1, 1. So that's this point here, 1, 1, 1. We want to convert it into polar coordinates. Well, the easy part is the x or the z value, right? When we go to cylindrical coordinates, that's just a 1 because z is just equal to z. Okay. The hard part is the r and the theta. So here we have z, and then we have here is r, and then this here is theta. Okay. So to do r, it's just straightforward. R is equal to the square root of x squared plus y squared. So that's just the square root of 1 plus 1. So we get the square root of 2. So the radius here is just the square root of 2. Now, if we want the theta, theta is a little trickier. Remember, theta is all of this stuff here. But basically, to start, you want to compute arctan of y over x, which in this case is 1 over 1, which is equal to arctan of 1. And if you remember your trig, arctan of 1 is actually going to be pi over 4. Again, that's not maybe that one you had to plug into a calculator. That's acceptable in this case, but basically, if you're looking for arctan of 1, then basically you're looking for something whose tangent is equal to 1. But if tangent is equal to 1, then sine over cosine is equal to 1, which means that sine is equal to cosine, and pi over 4 is where that happens. Also, from the picture here, you can kind of see, like, these are the same distance, so you get this right triangle. So it's a 45, 45, 90 triangle. So you know that has to be a pi over 4 angle. But in this case, since this is the first quadrant, this is exactly theta. So since 1, 1 is 1, 1 is in the first quadrant, then theta equals pi over 4. Okay. If it was in a different quadrant, then like we'd have to make sense of that angle that we got out of this, figure out how big it is. See, it's like, oh, is this too big? Like if it makes sense for the quadrant it's in, and then figure out, which of these, you can use this sort of as your guide to figure out, okay, if it's in the second or third quadrant, I just add pi. If it's in the fourth quadrant, I'm going to add 2 pi. Basically, if it's anything in anything other than the first or second quadrant, you're going to get, well, I guess if it's in the Second or fourth quadrant, you get something negative, and so you have to add pi or 2 pi just so that it's subtracting. If it's in the third quadrant, you get something positive, but it's smaller than pi, and you should be getting something bigger than pi. So you add it to pi to get something bigger than pi. I think maybe I'll do a recording of myself going through a few more examples here of problems like this that you can actually see it in action, because I spent a lot of time kind of flubbing over the formulas, and I'll record myself going through some of these examples here, filling in the rest of this chart, and then there's some more examples down here that I think will be helpful for your homework. I'll record that and get it posted before this weekend, and you guys can watch through that so that it's not so I don't completely leave you guys hanging. Sound good? Okay. Well then, if there are no other questions, we can wrap it up here, and I will see you all next week. Have a good weekend.